is looking at optimization of energy efficiency from, let's say, the comfort and other point of view, looking at the benefits and the comfort of the user, privileging his position, because in the end he's the guy who needs to pay for the car, and you have to convince him that it's a good thing. So on one hand, it's looking at the comfort, and on the other, trying to maximize the driving range of the vehicle. So looking at, I would say, at the holistic way. This is a fashionable word. So I would ask Ines Munoz, who's is working on the project. She's been at IDIADA for looking at management of different type of projects, from let's say air quality, water management, climate change, so a lot of different experiences. And thank you for being here, and the floor is yours.
Thank you. Okay. Good afternoon, everyone. Thank you for joining the last session of the day. Sorry, maybe someone can tell me what is my presentation?
Let me see where the presentations are. Oh. Was it under? Oh, great. From the Multi-Moby. No.
Yeah, this is
that was must be the previous one. That one.
that one.
Yeah, I think so. That must be ours, isn't it?
Yeah.
And this just or was there a second presentation on?
Yeah.
Click.
Then you click on the tab.
That's it. Thank you.
Okay.
Thanks. Okay, so hello again. My name is Ines Munoz. I work for AP Plus IDIADA. We were the coordinators of this project, and I'm here to present the main results of the DOMUS. DOMUS means Design Optimization for Efficient Electrical Vehicles based on user-centric approach. Just a few general details on the project. The project lasts 4 years. We had a 6-month extension due to Corona. It started in November 2017 and it finished October last year. We have a budget of almost 9 million euros and it was 100% funded. We were 19 international partners in the consortium, and you can see here the first picture in the kickoff meeting. These are the main objectives of the project. The main goal of the project was to reduce overall energy consumption for future electrical vehicles, and in order to do so, we have other sub-objectives, which included minimizing the energy consumption from the cabin, deeply understanding the user comfort perception, come up with design guidelines for future electrical vehicles that find a balance between the comfort and the efficiency. And also, for achieving all this, or as a result of all this, we develop an active system of hardware and software reacting to user needs and external conditions. So this is just a general overview of the structure of the project. The first line of the project, it was more centered in the virtual arena. The first step that we took was to develop 3D and 1D models, as well as safety, consumption, and comfort models in order to integrate them all in a virtual environment and being able to come up with different cabin designs, and also to being able to evaluate these interventions in terms of comfort, safety, and energy efficiency. The second line that you can see on the bottom of the slide was more focused on a physical environment. We actually designed and built, prototype, and integrated different hardware components into a Fiat 500e. So let me show you a video for one of the first results, tangible results we got for this project, and it has to do with a virtual mock-up, physical virtual mock-up in a full scale that we did during the project. So, let's play.
Current electric vehicle cabin designs are usually derived from conventional combustion engine vehicles that, having the engine as an abundant source of heat, have not been optimized in a way which enables electric vehicle efficiency demands to be met. Domos aims to generate designs of radically innovative, user-centric electric vehicle cabins that could help achieve such sustainability goals while achieving effective, safe, and comfortable experiences by vehicle occupants. As a result, 3 different cabin designs were conceptualized where Domos' innovative elements were combined with key innovation design modifications. The Domos consortium decided to make a mock-up of one of these cabin designs in order to show, in a full scale, the results of the design process to demonstrate the impact that the Domos approach has in electric vehicle cabin shapes and layouts, when the criteria of energy efficiency and user needs are placed in the center of the process. To this purpose, the vehicle is conceived as being equipped with autonomous driving features, which allow the passenger to either work or rest during the trip. To that purpose, the mock-up was equipped with a single reclining seat with a retractable work surface to accommodate a tablet or a laptop, and the steering wheel itself is foldable, allowing for the interior space modulation. The seat is designed to be lighter than customary, while granting a high passive safety level in the reclined position. A major contribution to the overall passenger compartment volume reduction is gained in a permanent way through the realization of a tunnel-shaped supplementary baggage compartment on the right front side cabin on one hand, and in a reversible way through a removable cabin partition comprised of insulating material on the other. Additionally, and to accompany this mock-up, an application was developed in order to control and trigger all the different cabin configurations in an easy, visual and intuitive interface. From this app, not only can the cabin configurations be controlled, but it also enables the user to activate all the climate control options that include the newly developed smart outlet blower and the radiant panels options inside the cabin. The disruptive design changes of this model allow for a significant weight reduction of the full vehicle, thus contributing to one of the main goals of the Domos project.
So that was one video. I have another one. Another main result of this project that I would like to comment regards one of the main results that we got was the result of the great collaboration between Virtual Vehicle and the Coventry University. And this main result is the integrated virtual demonstrator that we actually did for the FIA 500E, the prototype. What we did for this result is to use the simulation results from a 1D model of the HVAC system and the CFD transition simulation results for the cabin of the baseline vehicle and the cabin with the innovations. And we use a linear regression as machine learning approach to create a fast simulator of the HVAC system and the cabins. They were all integrated in a closed loop that allowed to actually test a simplifier control. Afterwards, the next step that we took was to develop a reinforced learning controller based also in machine learning. And this controller was used to optimize the performance of the Domus cabin in terms of an assessment framework. The assessment framework was a fitness function that we developed at the beginning of the project that considered elements as comfort, safety, and energy to balance the operation of the cabin. When all of this was integrated and put into work, we ran different simulations representing 28 different use cases representative of European conditions. And the results are the ones that you can see in the bottom left of the slide. As an average, the optimized reinforced controller was able to increase the range of the demo vehicle by more than 20%, comparing to the baseline. And when we ran the simulation considering the WLTP conditions, we were able to increase the driving range of the demo vehicle by 15%. It was also demonstrated that the reinforced learning controller, based on machine learning approach, performed better than the simple hand-coded controller. So as I mentioned before, we had a physical, tangible results for this project, which is a demo vehicle in which we integrate all the hardware and software innovations. And I would like to share with you again the last video in which you can actually see the demonstrator.
Range anxiety is one of the main barriers to electric vehicle adoption by the broader customer pool. Domos aims to deliver advanced solutions to significantly lower the energy demand for cabin conditioning by reducing the thermal losses of the cabin, the weight of the car, and finding innovating solution to warm or cool the cabin. All the innovations developed during the Domos project will be integrated in a demo prototype vehicle that will allow the validation of the technologies developed. These technologies include dashboard. The dashboard top cover was modified from the original baseline by changing the materials used in order to reduce the weight. The design was also changed in order to accommodate the human-machine interface developed for the Domos project. This newly developed interface is suitable for the operation of the systems, and it displays each component, allowing for an easy, intuitive, and precise control of all the elements. The design of the cross-car beam was also modified, as the passenger section usually made of steel was substituted with a lightweight material. Radiant panels. A set of 14 individual radiant panels made of printed foil heater have been integrated in the interior components of the vehicle. Active seats. The entire weight of the seat has been reduced by building a high-density steel frame, low-density foam, and new trim cover material. There is a heating mat in the cushion and backrest of the front row seats, and a radiant back panel in the passenger and driver seat. Also integrated is a cooling system, consisting of a lightweight fan and thermal fit air ventilation. HVAC unit. The HVAC has been completely redesigned in order to decrease its size and weight, and also to reduce its energy consumption. TES, Thermal Energy Storage. A thermal energy storage subsystem has been developed. With it, otherwise wasted thermal energy can be captured and stored. This energy can then be used to heat up the cabin. Insulation panels. The insulating panels were made with phase-changing materials and super insulation materials based on vacuum technology that exhibit very low thermal conductivity and a low density. Glazing. All glazed surfaces, windshield, rear window and door windows are fitted with electrical heaters and coated with a sun-reflective layer. And an efficient defogging and defrosting system of the glass has been integrated. Automatic control logic. In order to unleash the full energy-saving potential of these new active components implemented in Domos, the project introduces an automatic control logic capable of performing a real-time perceived comfort assessment of the passenger in the cabin and responding by determining the most energy-efficient combination of actuation parameters to all active components in the cabin. All this research and innovations will help Domos achieve its main objective of reducing the overall energy consumption of future electric vehicles, thus increasing the electric range in different climatic conditions, while maintaining comfort and ensuring safety.
Okay. So once the integration of all these components was completed, we performed testing and validation of the demo vehicle, and we did 3 different types of tests. The first one was acoustic testing. Then we also performed WLTP testing in order to assess the energy consumption. We did it at -10, 14 degrees and 35. And we also performed subjective testing. So the results of the acoustic testing, we place a noise source in the side of the panel, side of the car, sorry, and in the roof. And also we place microphones inside of the cabin in order to measure the acoustic intrusion. And in general, what you can see with the discontinuous line, that is the new configuration of the Fiat 500. That is the Domos demo car vehicle. And in general, the performance was better in the demo car, and that is mainly thanks to the insulation panels created and integrated by Hutchinson. That is another result for another acoustic testing. These are the best results that we got regarding the driving range, which again was the main objective of the project, to reduce the energy consumption of the cabin in order to increase the duration of the battery and the driving range. So the best result that we got was at the WLTP at 14 degrees, and we increased almost 10% of the driving rates, comparing the demo car with the baseline. We did so with a similar thermal comfort. The thermal comfort in this context, we actually measure the temperature, the air temperature in the baseline and in the demo in the passenger side, and they were all the same. Regarding acoustic comfort, we say it's a higher comfort because apart from the insulation that it was better, I was previously mentioned, also the blower and the compressor work less or a lower speed. So we can imagine the comfort in terms of noise was better. Safety and visibility, there was no windshield fogging in the demo car during the testing, and we also have a CO2 sensor implemented in the demo car in order to be able to activate as much as possible the recirculation mode, which of course saves a lot of energy. And the limit that we actually put in terms of safety was 2,500 ppm, and it never reached that limit. We also again performed safety subjective testing, and what we did is to measure the thermal comfort and the thermal sensation of the demo car in the street with a warm-up test, and we actually performed two tests, one with the radiant panels activated and the other one without the radiant panels. And it was we had 8 participants, different participants, and the results was that in general the thermal comfort and the sensation was reached faster and during longer time when the radiant panels were activated in the warm-up. I just would like to mention that during this 4 year of implementation time for the project, we have the chance to participate with other projects. For instance, we have a clustering workshop with Quiet Project, which is another H2020 project that has the same within the same call as Domus, and which had the same objective. It finished 6 months before we did. And we actually made parallel sessions per topic because we had the 3 main line of actions, which were thermal management, into the modification of the cabin, and virtual approach. And we also have the chance to have a stakeholder meeting with Biomotive, which is also another European project that are researching replacing the materials of the interiors of the cabin for another ones which are more eco-friendly. In terms of mid to long-term expected impact of the project, we believe we have actually contributed to the 3 main impacts we aim at the beginning during the proposal, which are increase the electric driving range. We didn't reach our objective, but we actually made progress in terms of simulation, and we have 2 different assessments of driving range in terms of virtual assessment, and also we have the real testing. We do not have the same results, but in all of them, we have positive ones. Regarding the impact for improved energy efficiency without compromising performance, safety, and comfort, we have developed 2 different controls that are actually developed within that with that criteria in mind, and that they have all been completed successfully. And we have also designed and prototype components, hardware components that reflect this criteria. And also in terms of solutions will improve the electrical vehicle competitiveness. We have already, and before the project was finished, there was and there is industry interest in the outputs of this project, especially regarding active glazing and the optimized controller developed by Coventry, and also from my side, IDIADA. We also are in private commercial projects at the moment regarding the automatic control logic that result from this project. And regarding the specific questions that actually the Commission asked for us, what are the future needs identified thanks to your European funded project? One interesting aspect that we would like to see is when the optimized controller developed by Coventry is implemented in an actual ECU of the car. That is going to be one of the next steps, and I'm almost done. And also we are involved in several proposals for Eurozone Europe that deal still with the thermal management. And in terms of how can other projects benefit from your activities, I know for a fact that, for instance, Coventry said that they learn a lot about how to work together, research institute and industry. And in general, every partner mentioned that thanks to this project, they accelerated the research within the company, minimum 6 months and maximum 2 years. Thank you.
Thank you also for the staying in time, even if we started a bit late. Now we are looking at another approach for again vehicle design. In this case, is a family of let's say purpose design vehicles, not adaptation of existing vehicles as in other cases. And about we are hearing about that from Professor Sorgnotti, who is at the moment is a full professor at the University of Surrey. Thanks for being here.
Thank you very much for your kind introduction. I'm very pleased to introduce Multi-Moby. Multi-Moby is a project that started on 1st December 2020, so we are still in the first half of its implementation. The project has a duration of 3 years, and the budget is approximately 8 million euros, with coordination by Infineon Technologies Austria. The consortium includes 9 participants. Essentially, the 9 participants cover the range of vehicle development skills that are needed. For example, we have participants such as Dana, TM4, and Valeo with expertise on electric powertrains. We have participants like Bitron with expertise on charging systems. We have participants such as Nanomotion with expertise on innovative sensors for driving automation. We have Altreonic working on innovative battery supercapacitor packs. We have expertise in advanced switching technologies for power converters, as well as my institution as academic partner. All this expertise converges into the vehicles, into the Multi-Moby vehicle demonstrators that are integrated by IFEVs, the SME that is at the core of this project. In particular, if we look at the objectives, the target of Multi-Moby is to develop a small fleet of electric vehicles. In particular, we are talking about 3 multi-passenger 4-door M1 vehicles with a 4-wheel drive on-board centralized powertrain architecture. So the motors are part of the so-called sprung mass of the vehicle, with 2 15 kilowatt, 100 volt, air-cooled, highly efficient powertrains that are based on permanent magnet-assisted synchronous reluctance motors, so with low content of rare earth materials. And then, to complete the fleet, we have 3 multipurpose vans, in particular an L7CU prototype, which is also 4-wheel drive, with 2 7.5 kilowatt 48 volt air-cooled powertrains and a low-cost belt-based transmission system. And 2 M1 versions, again 4-wheel drive, one with 2 15 kilowatt 100 volt air-cooled powertrains, and the second one with 2 15 kilowatt 48 volt liquid-cooled powertrains. One of these multipurpose vans targeting the transportation of general goods, while the other 2 vehicles will target the delivery of food. And here we can see 2 rendering pictures that were included at the submission time of the project proposal, but we can see here a photograph of the current generation of the electric vehicle prototypes of Multi-Moby. Multi-Moby covers a lot of areas that are required for systems integration at the vehicle level. In particular, Multi-Moby includes electric powertrain optimization. In particular, in this area, we have a continuation of the activities that started in the previous European project TEL. as I said, there is the development of 100-volt powertrain by Dana TM4 and two 48-volt powertrains by Valeo Powertrain Systems. And the development process of the electric powertrains is based on simulations, digital twinning, optimization. For example, in this picture we can see a motor, rotor, and stator topology sensitivity analysis that was carried out in order to understand the sensitivity of the geometry of the rotor and the stator of the motor with respect to the energy loss during a driving cycle, as well as with respect to the variation of the peak torque and the torque ripple of the machine. So this virtual process of optimization of the components is followed by implementation of the hardware, installation on the vehicle demonstrators, and finally testing. So here we can see some of the pictures of the prototype components that have been provided by the relevant participants. We can also observe a preliminary installation of one of the electric powertrains on an initial prototype of the electric vehicles by IFEVs. And then we can see, for example, a picture of a preliminary testing session on the rolling rod facility at IFEVs of the so-called mule vehicle, that is a preliminary version of the demonstrator vehicle, and this activity also involves some form of testing on tracks or proving grounds. Another very important aspect of Multi-Moby is the enhancement of safety. Safety, first of all, in terms of passive safety. This aspect has been dealt with, in particular, by the participants CIDAUT. CIDAUT have designed, together with the HIFERS, a high-strength steel structure combining low cost with high energy absorption capability and stiffness. This is a follow-up of a previous FP7 project called Plasmoby. And in this steel structure of the chassis, different products of the dual-phase steel family are combined. And the activity consists of finite element analysis, including physical crash tests at the CIDAU facility. So here I have included some of the pictures of the models that have been used within the structural optimization of the chassis. And then at the end of 2021, also some pictures of the physical crash tests that were carried out at the CIDAUT facilities in Spain. I have discussed passive safety. Another essential aspect in light electric vehicles is active safety. Differently from other projects where the approach is to target high segment vehicles characterized by very complex as well as expensive chassis actuation systems, in this specific project, as low cost is an essential point, we are trying to implement smart solutions that do not imply significant additional hardware cost for enhancing active safety. One example, among various others, is the preemptive trail braking control function. So the basic fact is that nowadays, if we have a car with a conventional stability control system, the control system is a reactive system. So if a driver approaches a corner at excessively high speed, the stability control system, once the vehicle tends to become unstable within the corner, tries to actuate the friction brakes individually in order to keep the so-called side slip angle and the yaw rate of the vehicle under control. In Multi-Moby, we try to implement a solution based on predictive control. So nowadays, through the GPS, through the navigation system, it is possible to know in advance what the future trajectory of the vehicle is likely to be. So it is possible through a preemptive controller preemptively slow down the vehicle if the entry speed into a corner tends to be excessively high. So this is a rather simple functionality that, of course, implies some form of vehicle connectivity and predictive preemptive control, but this gives a functionality without additional hardware cost, without a functionality that goes beyond the typical functionality of a conventional stability controller. So in Multi-Moby, we have further developed this control function. First of all, by evaluating it through vehicle dynamic simulations. For example, these plots are about an obstacle avoidance test in which the vehicle has to change lane and then go back to the initial lane from the maximum speed in order to stay within the limits of the trajectory. And we can see that if we look at the speed profile, V is vehicle speed, the preemptive braking controller slows down the vehicle before the vehicle enters the obstacle avoidance course. And very interestingly, in the predictive controller that we have tested here, we have also imposed some constraints in terms of lateral dynamics. For example, in terms of maximum value of the so-called size dip angle beta that tells us how much the vehicle is sliding laterally during a corner. So essentially, we can achieve the same functionality with much more complex systems without having significantly complex actuation hardware. And in the first part of the project, after running some simulations, we have also preliminarily implemented this function on a light electric vehicle demonstrator. For example, these are experimental plots obtained in the car park of our university of a U-turn test, so X and Y indicates the trajectory of the vehicle, in which the driver tries to accelerate the vehicle during a U-turn test. So we can see that the passive version of the vehicle is characterized by a progressive acceleration, but the vehicle speed is excessively high with respect to the turning radius. As a consequence, the vehicle without the controller cannot stay within the lane. Whilst with the different versions, pre-RB, that is a rule-based version of this preemptive braking controller, with the so-called PM and MPC, that is a simplified version based on nonlinear model predictive control of this preemptive braking controller, and with the DT and MPC, that is a double-track model-based nonlinear model predictive controller version of this functionality, we can see that the vehicle can follow the reference trajectory. The vehicle is slowed down when it is necessary, but then at the exit of the corner, the vehicle is reaccelerated because the controller deactivates. Another example of the presentation seems to be stuck. No, I don't have any video in this presentation. I don't know why. Hopefully. Another example of a smart control function that has been developed within the project TEL, but now it is transferred to Multi-Moby, is the preemptive traction control function. So essentially the idea is that in future, thanks to vehicle connectivity, it will be possible to know in advance the presence of low friction patches on a road. So it is possible, for example, to pre-alert the traction control system regarding potential hazardous situations in terms of tie rod friction conditions. So in TEL and then in Multi-Moby, we have implemented, first of all in simulation, and then also tested experimentally, a nonlinear model predictive controller that works under the assumption that we already know in advance the friction coefficient profile of the rod in front of the vehicle, And as a consequence, we can change the reference slip ratio as well as the so-called prediction model of the model predictive controller that runs in real time on the vehicle in order to preempt these friction transition events. And we have tested this functionality again, first of all, on a light electric vehicle in our car park. Then once the functionality was calibrated, we also transferred it to the Multi-Moby vehicle in IFES. And here we can see some plots of the experimental results where we have a comparison between the passive version of the vehicle, so without any traction controller. In particular, I would suggest to have a look at the last plot that plots the so-called sigma x front right variable. So this is the so-called slip ratio of the front right tire. In particular, we can see that the passive vehicle has a significant with slip when we have the transition of rod mu from high to low, whilst the vehicle with the so-called NMPC, that is a sort of conventional benchmarking traction controller, can manage to control the slip, but there is more or less half a second of time in which the controller cannot deal with it because of the delays of the electric powertrain, whilst with a preemptive controller that corresponds to the blue line called pre-NMPC, we have a preemptive compensation of the tire slip event with the consequential benefits in terms of longitudinal and especially lateral vehicle dynamics. So these are only examples of the many functionalities that are and many items that are being tested and developed within Multi-Moby, because there is also a lot of work, for example, in the area of charging, of battery charging, in the area of hybrid energy storage that I haven't even mentioned. In terms of impact, well, for sure there is a significant industrial impact in terms of vehicle safety, both in terms of passive and active safety. Multi-Moby will also implement in the second half of the project some form of driving automation function, but we are still in the process now working on those. Then we have impact in terms of energy efficient electric powertrains for 100 volt and 48 volt applications with limited content of rare earth materials, hybrid energy storage systems, and of course the vehicle level, simple but smart vehicles with best-in-class energy consumption characteristics. And last but not least, IFES, thanks to the background of previous European projects, is experimenting a microfactory concept for low investment localized production. Finally, I would like to mention the fact that we try to generate also some academic impact to have a long-term spread of our research in the community, in the academic community. For example, in the first project year, we have produced 3 journal papers. Thank you very much for your attention. As a last point, I would like to mention that we are part of the so-called Evolve cluster that includes 8 European projects on the topic of vehicle electrification. So we have already implemented some joint workshops to disseminate our results.
Thank you also for staying within the time. So we have a good time for question and answer. So I pass it to Aldo to manage it.
Thanks a lot. Yeah. Also welcome to my side to the last questions and answer section of our today's sessions. My name is Aldo Offenheimer. I'm coming from Virtual Vehicle, Graz, Austria, and the floor is open. Happy to take your questions for both of our presenters. Yeah. Thank you, David. Thanks a lot. Microphone is coming.
Yeah, thank you, David Storer from CLEPA, the Association of Automotive Suppliers. So this is a question for Ines about the Domus project. You showed about a 10% improvement in efficiency and therefore improvement also in range. But there were several interventions that were put together to achieve that. Which do you think are the most effective interventions?
Okay. Hello, David. Well, what we know is, for instance, one of the most effective interventions of Domus were the active glazing. It was possible, thanks to the heated windows, to get rid of the HVAC in the misting or the fogging. And the recirculation mode was also a key factor in saving the energy. So I will say those two were the most successful. In terms of active seats, this is not from the actual testing. This is also from the pre-calibration testing we did for the automatic control logic. It was also discovered, or this is our conclusion, that the local comfort of the active seat was not fairly represented in the comfort score, especially for the conductive heat. And it is believed that the local comfort in the back and in the pelvis area, it has actually a higher comfort score that it will be interesting to research more. And also the radiant panels. The radiant panels, they didn't really consume that much, also because in the test, the target temperature was 22. It was believed that if we kept it at 18, it might have actually reached a higher, let's say, energy decrease. And it was also comment that the size of the radiant panels could also be investigated further in terms that if they were bigger and the target temperature higher, it will actually maybe help more in saving energy. So.
Can I just
Obviously, we have enough time. David, just
No,
go
I
on.
just wanted to say, so all of these interventions are relatively low cost. That they seem to be quite affordable. If we're talking about radiant panels and the glazing and also the control, would you say that's true, that it's affordable, or do you think it might be quite expensive to achieve that?
Well, what I do know is that it's also a further step to be taken regarding the electric integration, in order to actually reduce all the ECUs and the cabling and all that. So I think that's actually an important step of improvement. We actually perform a cost-benefit analysis, and it didn't really show that at the time it's affordable, all of these interventions together in a car. So that is actually something to work on. But what I can recall at the moment, especially electrical architecture, the integration and simplification of electrical architecture is a big step to take in order to actually make more affordable and less heavier the car also, because that was also an issue. So many cables.
Okay. Thanks a lot. Further questions? Yes, please.
Also for Ines, with some of the partners within your project, we also had another project called OSMEV. In the OSMEV, I remember a very nice discussions when making the simulations on how to save energy in terms of thermal management. The first thing to do that costs nothing is selecting the color. If you live in a hot country, have you ever been in Abu Dhabi or Saudi Arabia and the like?
Not yet.
You will never see a black car, all white. If you live in Spain, in Italy, in Greece, okay, most cars are white. You save 20% doing nothing. Why? The second point, almost doing nothing. No, it's not. The second point is this. In an electric vehicle, to recover thermal energy is extremely inefficient. And the thermal storage is also extremely inefficient. So it is a good exercise, we did it, but at the end, it is no sense. From an efficient point of view, okay? That's just little consideration, okay?
May I add on the top?
Sure.
Yes, but most of the interiors of the car are black. Therefore, they are capturing energy. And also, don't let you find your mobile phone when it drops inside. Sorry for joking.
Thanks a lot. So, any other questions? We still have a couple of minutes. Some other questions?
If there are none,
Yeah.
I would have one. You mentioned, maybe I didn't get.
Yeah,
About the recirculation. What CO2 level you were using as a trigger?
2,500 ppm was the limit. If we reach that, we'll consider the safety.
As far as I remember, this starts to be already beyond what affects the brain function. So maybe do a kind of sensitivity, because if I remember correctly, 1,000 ppm is already affecting the response time and things like that. So I don't know if you have looked at, but see in case with a couple, 2 or 3 different concentrations, what the effect is, and then check with the employment physicians or something like that. Because I remember that 1,000 was already on the risky side.
I'm not saying we reached that during the testing. I know the drivers were okay, but I will.
No, but okay, if that is a trigger function. Because on a long trip, maybe with 3 or 4 people, you could.
No, it's interesting observation.
Quite fast. And about color. Sorry, I was in aeronautical industry, and there was one guy that wanted his Learjet blue, dark blue, and he had no problem paying $1 million for having reinforced air conditioning. So, it's all relative.
Thank you. Are there any other questions? Otherwise, I would have one for my name colleague Aldo. Just it's not so technical, but I was just looking when watching your presentation, you made use of quite a lot of different European projects. How did you manage to really get that integrated, let's say, in such a follow-up project? Have there been partners already involved which have been in this previous project, or have there been somehow a technology transfer? Maybe you just can elaborate a little bit on that.
Well, in Multi-Moby, there are participants who have already collaborated in several previous projects, and we are quite used to working together. And essentially, we try to further develop some of the ideas that have been preliminarily elaborated in previous projects. For example, in Plasmoby, there was a preliminary design of the steel structure of the chassis of the vehicles that are now the Multi-Moby vehicles, but no physical crash test had been implemented. So in Multi-Moby there was a further optimization in the initial part of the project, and then at the end of the first project year there was the physical crash test implemented that confirmed the simulation results. So essentially some of the partners, some of the key partners bring some background, and of course in terms of IP there is the consortium agreement that regulates the background and foreground of the projects, and these ideas are further developed, increasing technology readiness.
Okay.
Since you mentioned the crash, can you tell us what let's say, equivalent Euro NCAP stars you achieved?
Well, here we have Javier Romo from CIDAL, who actually was on the crash, but correct me if I'm wrong, we are talking about 4-star Euro NCAP result. Is it correct?
In Plasmoby, we are targeting 4 stars in Euro NCAP, but also we have to we are talking about, let's say, the structural test. Euro NCAP is nowadays is more complex than several years ago, so you have to evaluate many different parameters, not only crash behavior. You also have automated driving, like
no, just the crash part, let's say, of the Euro NCAP. I know that now with active you have cars that have 4 stars and now are 0 or 1, so that's another story. But on the crash, on the old one, let's say,
we are focusing on 4 stars.
But the crash you did, where you get?
The crash we did was really nice. In the front against a rigid wall, we have some small issues that are registered in the due to some let's say small defects on the prototype. In the offset, we were on the line to get the 4 stars, and in the lateral crash also we are in the score to get the 4 stars.
And I mean, the previous projects were L7. This is for on the L7 or on the M1 structure.
This is M1.
Okay.
Yes, we are with the parameters of the M1. Yeah.
Thanks.
Tomorrow you will see all the videos. And this is really the state of the art. I was saying taxpayers are well spent. The activity done and see that really fantastic. But tomorrow you will see all the videos. The results are state of the art in the world for small cars.
So there we have some announcement of tomorrow's videos. That's good. Any other questions from the floor? I'm happy to take them. I think one or two we can still accommodate. Some more?
7 minutes. Otherwise,
Otherwise we close. Yeah. If there are no more questions, then I would say thank you again to our presenters coming here presenting their projects. And from my side, and then also from Maurizio's side, we just can invite you now for the next on the program. So it's join main stage again downstairs, and there is this short signature ceremony, and afterwards there will be cocktails served. So that's it. Have a great evening. Bye-bye.